All right, AP Chemistry, we're on to the third lesson in the kinetics unit. This is on the integrated rate law. So we'll talk about in this lesson what's the difference between the integrated rate law and the rate law that we did in the last lesson. All right, so first we need to learn a little bit about how to deal with logs and natural logs. A couple of these problems you can delete. This one didn't have a log in it, and these are duplicates. Okay, so we'll just start up here. So whenever you have an exponent or a variable in the exponent and it's e raised to x, you create a log on both sides. So it's ln Okay, so e and ln are inverses of each other, just like multiplication, division are inverses, or addition, subtraction. So what that'll do is these will cancel out and the 2x comes down out of the exponent. And then you go on your calculator and you calculate what ln of 8.1 is. So on this calculator, ln is right there. It's ln. Get it on here, get that turned on, ln. And we put in 8.1, close the parenthesis, and you get 2.09. We'll just call it 2.1. So divide both sides by 2, and you get x equals 1.05, something like that, okay? All right. Over here, same kind of problem, except you got a coefficient out front, so divide both sides by 2.3. Cancel, and I'll come up here to work up here, e to the 3x, and 4.1 divided by 2.3, and that's going to give you 1.8. All right. Okay, so you get that. So now we're going to take the natural log of both sides. Alright, and this just, again, the ln and the e inverse each other, so you end up with just 3x. And the natural log of 1.8 is going to give you 0.59. And so divide both sides by 3, and you get about x equals roughly 0.2. Alright. Let's come down here. Now you have a natural log and you have an x inside of the natural log. So you inverse by making both of these an exponent of e. So I'm just going to shortcut here and make that an e and that e to this. So e to the natural log of 2x cancels or inverses and simply gives you 2x. And e to the 3.2, so you come over here, you hit second, and then you hit ln. And the secondary function on ln is e to the x. So now you can put in the number 3.2. And that's going to equal 24.5. So we'll just call that 24.5. Divide both sides by 2. And you get x equals about 12.25. Okay. Right there. All right, let's do this one. Again, we can raise this e raised to that, e raised to that. So e ln inverses, so you simply end up with x on this side. And again, to get the e, you hit second and ln, and then you put the 2.5 in, and that gives you 12. In round numbers, 12.2 actually. Okay. And that's your answer. All right, this one, 3 ln x to 27. So first you divide by the 3, and you end up with ln x equals 9. So it's e raise that, e to that, e to that, e to the 9th. And the e ln x becomes x, and e to the 9th. Do that to the 9th power. And you get some big number, 8103. Okay, and that's the answer there. All right, let's keep going. If you have questions on these or need some practice, come in for tutoring. Okay, write the equation for first order integrated rate law using simulated reactants A and B. Well, none of the problems they give you in integrated rate law is going to have two reactants. They usually just deal with one reactant and it's A, so you won't ever see a B. So identify and explain each of the variables. All right, so if we go back on the last page, you have a reference sheet. It's just that. It's not a problem set. And it says a first order reaction produces a straight line when natural log A, that should be is plotted against time. So here's the reaction of a first order reactant. It follows a curve like that. It's steeper up here because there are more reactants, and the reaction happens faster when there's more molecules to bang into each other. So steeper curve part of the curve means it's faster. Flatter part of the curve means it's going slower because there's fewer reactants to react. Now, if you take the natural log of this and the initial reaction, this right here, then you end up with this equation. Natural log of A equals negative KT plus natural log of A naught, or A0. That's the initial concentration. Well, this follows a slope-intercept form. Y equals mx plus b from algebra class or from math class. So b, this is the y-intercept right there. Okay, m, this, the rate constant, the negative rate constant, is the slope. So you can see right there that I'd already written it in here. The slope is negative of rate constant, and so that's the significance of this. This is a way, if you can linearize this, what that does is you know that the slope is going to be the negative of the rate constant. Now, rate constants always have to be positive, so you simply, to know the rate constant, have to take the negative sign off. But that's the significance of using logs. Logs linearize curved lines. Not any curved line, but curved lines of certain functions, and this would be one of those functions. Okay, so that's the purpose of using logs. All right, so you just simply come back and write this equation, the part in red, on the for the problem. So I'm going to come back here, and it's going to be this. Now, some of the versions of this, this ln got left off. It just said A0. It should be natural log of A0. So if you have one of those, correct it. The later versions, I corrected it myself. Okay, so there you go. So this is the concentration at a particular point in time t. And so if you take t and multiply it by the rate constant, and you're going to get a negative number, so you subtract that from the initial reactant. This is always going to be the highest value of the reactant because you haven't used any of it up yet. So you take this and subtract this, and that'll give you the natural log of the concentration at some particular time t. Now, when you get that, you're going to want to inverse this and make it e to the ln concentration of A, because you don't care about the natural log of A, you care about A, that you want to know the concentration. But that would be the formula, so that explains what each of these variables are. Okay, we'll keep going. What is the difference between the time-independent rate law and the first-order rate law? So the time-independent rate law, the one we did earlier, which looks something like this. So you'll notice time is no part of that equation. It's purely a function of concentrations of A and concentrations of B. And again, in this one we have more than one reactant usually. It doesn't have to. It could. It could have more. So A, B, we can even have a C. Okay, so this is not a function of time. It's a function purely of concentrations. Again, I'm saying that. I want you to write it down. Okay, I don't want it to be a copying exercise. Now, for the first order integrated rate law, it's simply this up here. So this is a function of time. It tells you what concentration you're going to have if you start with this concentration and then you subtract, because this is a negative sign, KT, it'll tell you what the concentration is at this point in time. Okay, and then you need to, obviously, as we said, raise e to this power. You don't want to know the natural log of A, you want to know A. So we said that before. Okay, so this is this is the concentrations between two different points in time. All right, so that's what this one is, and this one has nothing to do with time. It's simply based on concentration. Okay, 4. Use the analogy of velocity of a car to explain the difference between time-independent rate law and integrated rate law. So the time-independent rate law, this one we said, is at a specific point in time. It doesn't depend on time. It's whatever the concentrations are. So it's like looking at the speedometer of a car. If you look at the speedometer of the car, it tells you the time at a very specific moment in time. The velocity at a very specific moment in time. Whereas this one is more like if you went from San Diego to Los Angeles, 100 miles, and it took you 2 hours, well, that would be 100 divided by 2 would be 50 miles per hour. It kind of tells you, based on a certain amount of time, how far you're going to go. Okay? So this one involves time and two different concentrations. This involves concentrations only. All right, so kind of put that in your own words and write it down. All right, what is the rate constant? It is a number that's a function mostly of temperature, but we'll study some of the other things that are involved in it that tells you how fast the reaction is going to take place, what the rate of the reaction is going to be. What part of the graph is represented by the rate constant? We just saw that. It's the slope. If it's positively sloping, that would be a second order reaction, or it's the negative slope if it's first order. Okay, so the slope or the negative slope, you just take the negative sign off, will tell you what the rate constant is. Number 5, describe what happens when the rate of a reaction when the concentration of a reactant of the following order is double. So 0 order, there will be no change in the rate of the reaction. A 0 order reaction is not at all a function of the concentration. Whatever the concentration is, the rate stays the same. First order, if you double the concentration of a reactant, you double the rate. So you have twice as many molecules, so they're going to smash together twice as often, and the reaction is going to move twice as fast. That's the way to think about it. For second order, that's going to be a function of a square, the reactant raised to the second power. So if you double the concentration of a second order reactant, you will quadruple 4 times the rate. All right, down here you can see I already started this one for something else. So what is the half-life formula of a first order reaction? And this is a fixed formula. And does this apply to 0 or second order? So this is it. So this symbol means the time of a half-life. That's what that notation means. It's always this number, 0.693, divided by the rate constant. So I came over here and I did a little example of a first order reaction. If you have even time intervals, it could be 0, 1, 2, 3, 4, or it could be 0, 2, 4, 6, 8, which I used here. You have even time intervals. And what it means is for the same time interval that the concentration will be cut in half. So from 0 to 2 minutes, it will be cut from 16 to 8. From 2 to 4 minutes, which is also a 2-minute interval, it will be cut in half again from 8 to 4. From 4 to 6 minutes, that's another 2-minute interval, it will be cut from 4 to 2. And from 6 to 8, another 2-minute interval, it will be cut from 2 to 1. So this would be an example of a first order half-life. The interval time intervals, an even time interval, the same time interval is what I should say, a same time interval will produce a half-life. In this case, the half-life of this reaction is 2 minutes. Every 2 minutes, the reactant gets cut in half. Okay, so you simply plug in the K. If it gives you the K, you plug it in, and you can do that. Let me show you how to do a scientific notation in case you're still not comfortable. Okay, so I'm going to put a parenthesis, 0.693, close the parenthesis. Maybe you have to do that, maybe you don't. I think it's a good idea. Divided by parenthesis, and it's 2.1 times 10 caret negative 4, close the parenthesis, and what you get there is 3,300. Okay, and I didn't put a unit of measure. I should have. We'll say 3,300 seconds, which is about a little less than an hour. Okay? All right. What is the value of K for the reaction with a half-life of 2,500 seconds. So you can go ahead and rearrange the equation. Okay, I'm going to multiply both sides by k and divide both sides all in the same step by 1t1/2. Okay, this goes away and this goes away, so what you end up with is k equals, and they gave you t1/2 is 2,500 seconds. Okay, so go on the calculator and do that. And we get 0.0, pretty short half-life. Excuse me, pretty small rate constant is what I should say. We have the half-life. And I'm just going to call it 2.8 and leave it at that, okay? Now, if it's first order, it would be 1/seconds is the units of measure. Okay, so you should kind of get those memorized, those units of measure for 0 first, second order half-lives. Okay. This is one I told everybody. I don't know what I had here. Use separate graph. I don't know. I think I deleted a question that was applicable to, so we're going to forget about that and move on. Okay, now I gave you a series of these to determine, based on the graph, whether this was a 0th order. So if it's just straight up, notice you have even time intervals. So is this 0th order? That is, if these form a straight line, and we'll talk about that in a second, and then it's 0th order. This is first order because it's natural log. It's a function of natural log. And this is second order. It's 1 over the concentration. So what you do is you do these. It's a little bit of arithmetic, you know, crunching your calculator until you find the one that it is, okay? All right, so the first thing you want to do is find the differences. If the differences, think of this as the x-coordinate on a graph, and this is the y. This is linear, 1, 2, 3, 4. If the differences here are the same, whatever they are, then that means this would also form a straight line with this. Okay, even intervals here, and that means it would be 0 order. So let's go ahead and we're going to do 4.95, and I'm going to stop the video so you don't have to take time with my calculations. I'm going to come back. So what I'm going to do is say 4.95 minus 3.32, put that number right here. 3.32 minus 2.23, put that number right here. 2.23 minus 1.49, put that number right here. And if those numbers all are even, or are pretty much the same number, it means these intervals are even, and it means it's 0th order. So let's go ahead and do that. Okay, so I did that for the first two, and I saw I got a difference of 1.63, and here I got a difference of 1.09, so I can see that's not going to form a straight line. I don't even need to do the third one. So now we're going to come over here, and we've got to compute the natural log of each of these numbers. So I'm going to take the natural log of 4.95. So ln 4.95, that gives us 1.6. Now I'm going to stop the video and I'll do the rest of them very quickly. Okay, so these are the natural logs of each of these. So natural log of 4.95, 1.6, of 3.32, natural log is 1.2, natural log of 2.23, 0.8, and of this one, 0.4. So if you look at these differences, they are all the same. 0.4, 0 between 1.2 and 0.8, 0.4. It's a negative because, remember, first order is downward sloping. So let me go ahead and put the negative sign on there just to be proper. And this is going to be negative 0.4. Anyway, the differences are all the same. That means this is a first order reaction. Okay? You don't need to do this one. Once we found its first order, it can't be both first and second, so you can move on. Okay, let's go on down here. Yeah, let's see about the differences for just straight up the concentration. So it's 3.33 minus 1.25. Okay, and this gives us 2.08. 1.25 minus 0.77. I can see that's going to be a lot less than 2.8. It's going to be about 0.48. So I don't even need to go any further. It's definitely not going to be this. Let's come over here. Again, we have to take the natural log of each of these numbers. Natural log of 3.33 is going to be 1.2. Okay, I'll stop and do the rest. Okay, these are the natural logs of each of these. The difference between these two I can see is about 0.98. Okay, between these two is going to be about I don't know, 4.546, something like that. Okay, here I'll just prove it to you. 0.22 minus negative is a plus. 0.26, and that's going to give you 0.48. So I can see these differences are not the same. 98, 48, no, that's out. So let's try this. Now there's no guarantee this is going to be it's going to be second order. Okay, but we're going to take 1 over each of these concentrations. So let's go ahead and do that. So 1 over 3.33. The way you can do that is just do 3.33 and then hit the x to the negative 1. That's the reciprocal. That's 1 over, and that gives you this. Okay, I'll stop it and do it for the rest. Okay, so these are the numbers I got when I took the reciprocal, flipped over each of these, 1 over a, and you can see they have common differences, 0.5, 0.5, and so on. Okay, so this is a second order reaction. All right, we'll keep going. Okay, we come down to this one, and finally we get an easy one. 4.8 minus 3.9 is 0.9. You can say it's negative. 3.9 minus 3.0 is negative 0.9. 3.0 minus 2.1 is negative 0.9. So these differences are the same. That means this is going to be a 0th order reaction. Okay, go on. You don't have to do these. Okay, so I look at these. I can see these differences aren't the same. 30 to 20 is 10. 20 to 13.5 is 6.5. 10, 6.5, not the same. So it's not going to be this one. So we're going to take the natural logs. I think you kind of get the hang of this, but I want to be sure you get the answer. So I'm going to go ahead and take the natural log of 30. And we get 3.4. And I'll stop the video and do the others. Okay, there you can see the natural logs of each of these numbers, and you can pretty easily see there's the same difference, 0.4, 0.4, 0.4, so this is first order. You don't have to do that one. Okay, we'll move on down, and let's see if we have the same differences. 0.9 to 0.56 is going to be 0.34. 0.56 to 0.4 is 0.16. Those aren't the same, so it's not going to be 0 order. So again, we're going to take the natural log here. Okay, so here is the logs of these numbers. So this first one is going to be 0.47. The next one, 57 to 91, is 0.34. Let me just do the last one. And from 91 to 17, so it's 0111, it's going to be 0.26. So that's not going to, those don't have same differences. So now we do 1 over each of these. 1 over 0.9. And we get 1.1. Okay, I'll stop the video. Okay, so I see this is 0.68. This is from 78 to there is 0. What is that? 78, that's 80, that's 70, 72. So those aren't too far apart. Don't rule that out. This is 73. So I would say those line up pretty well. It's rarely going to be perfect in the real world. So we're going to say this is second order. Okay, boom. That's it. That's how you do these. And that's the end of this lesson.